Talk about sequences today, class 26. Today's activity is long, so we'll get through the demo as quickly as we can. So today we're going to leave integrals. We're moving on to a new topic for the next 4 weeks. We've been working with continuous phenomena, things that happen all the time, like water flowing over a dam is a continuous process. But for the next few weeks, we're going to focus instead on discrete phenomena, meaning phenomena that occur at distinct moments in time, every second or each day, or once per month, something like that. So there's lots of new vocabulary and notation at the start of these few weeks. So try to stay in the habit of using correct calculus notation. So what is a sequence? It is just an infinite ordered list of numbers. So our first example would be 1, 3, 5, 7, 9, etc. You could think of a sequence as a function, but the domain is just the positive integers. The only numbers that you input are the positive integers. So if my sequence is 1, 3, 5, 7, 9, my inputs would be 1, 2, 3, 4, 5, and 1 goes to 1, 2 goes to 3, 3 goes to 5. So calling the sequence A, we could use standard function notation. A of 1 is 1, A of 2 is 3, A of 3 is 5. Right? So when you plot the first number in the list is 1, the second number in the list is 3, the third number in the list is 5. But more common is to use the notation where the subscript is the counter. Instead of putting the input in parentheses, you put it in a subscript. So A sub 1 is 1, A sub 2 is 3, etc. So A of 7, that means the 7th number in the list of odd numbers. So 1, 2, 3, 4, 5, 7, 9 would be the 7th number in the list. Right. Oh, whoops. Wrote that in the wrong list. 1, 3, 5, 7, 9, 11, 13. So 1, 2, 3, 4, 5, 6, 7. The 7th number in my list is 13. A sub 100. What's the 100th number in the list of odd numbers? 199? How'd you get that so fast without writing them all out? It might be 199. How did you do that so fast? Times 2 minus 1, yeah. So it might be helpful if we actually wrote the general term first, a formula for A sub n, and we would look at the input and how would you create the odd number associated with it, right? So 1 becomes 1, 2 becomes 3, 3 becomes 5, 4 becomes 7. So each output is twice the input and then subtract 1, right? So 4 times 2 is 8. Subtract 1 to get 7. 5 times 2 is 10, subtract 1 to get 9. So they're all 2 times the input and then subtract 1. So to get A sub 100, 100 times 2 is 200, and then subtract 1, 199. So some vocabulary. A sub 1, that's the first term in the list. A sub 2 is the second term. A sub n is called the general term. 2 times 1 is 2. Subtract 1, you get 1. So a sequence can either converge or diverge. A convergent sequence is one that approaches a single finite limit as n goes to infinity. And a divergent sequence is one that either approaches infinity or just does not approach a single limit as n goes to infinity. So let's look at a couple of example sequences. I've given you formulas for the general term, and we want to determine if each one is convergent or divergent. We'll start by writing out the first 4 terms of each sequence, and then if the sequence is convergent, we'll determine what it converges to, what the limit is as n goes to infinity. So my first term in the sequence, a sub n, is n over n squared plus 4. A sub 1 would be 1 over 1 squared plus 4, which is 1 over 5. A sub 2, 1 over 2 squared plus 4. Sorry, 2 over 2 squared plus 4. So that's 2 over 8, or 1 over 4. A sub 3, 3 over 3 squared plus 4. So that's 3 over 13. And a sub 4 is 4 over 4 squared plus 4. 4 over 20, or 1 over 5. All right, so what can you say? Are those all right? Anybody catch me in a mistake? Looks okay? Okay, good. All right, so what do you think the limit is as n goes to infinity? Let's write out what we're looking for. We're trying to evaluate the limit as n goes to infinity of a sub n. So that's n over n squared plus 4. Limit as n goes to infinity. Yep. Yes, yeah, because when you're talking about infinity, the 4 is just like super not important, right? So this would reduce to, this is the same thing as the limit as n goes to infinity of 1 over n. And what is that? 0, yeah. When the denominator is getting really, really big, the value of the fraction is getting really, really small, so the limit is 0. So this converges, and it converges to 0. Okay, let's look at the other one. A sub n equals 1.2 to the n. So a1 is 1.2 to the first, or 1.2. a2 is 1.2 squared. Thank you. A3 is 1.2 cubed. And a4 is 1.2 to the fourth. All right, what do you think? The limit as n goes to infinity of 1.2 to the n. Infinity, yeah. If you continuously multiply by 1.2, the values are just going to grow and grow and grow, because 1.2 is bigger than 1. So we say this sequence diverges. Okay, so it turns out that you can show a sequence converges even without being able to show what it converges to, if you know that it's bounded, meaning there's some upper value that it can't ever get past, and monotone. So monotone means always increasing or always decreasing. So always increasing or always decreasing is monotone, and bounded means that it is sandwiched between two values. The sequence is sandwiched. No, there's no H in sandwich. Is there? No. Yeah, that looks better. Sandwiched between two numbers. So if I draw a picture of what this is, so here's n, a sub n, if I know that a sub n is trapped between two numbers, it's sandwiched in here, and I know that a sub n is always increasing, it's always getting bigger, or it's always getting smaller, then it must be convergent. It must have some limit. All right, so let's think about the sequence 0.19. So this is just a list of numbers. First number in the list is 0.19. The next number is 0.1919. Then 0.191919. Then 0.19191919. We want to decide if this converges. And the limit of this sequence, what it would converge to, is what we mean by the notation 0.19 repeating forever. So what this converges to is 0.19 repeating forever. Does that converge to a value? Yeah, so it's bounded, right? So a sub n is always less than 0.2, right? It's always bigger than 0. So it's trapped between 0 and 0.2. And every time I go to the next term in the sequence, it gets a little bit bigger, right? I'm adding a little bit to it. Another 19 on the end makes it a little bit bigger. And always increasing. So that tells me that it converges. There is some limit that it's approaching, and we will be able to find out what that limit is after next class. Okay, but you should keep in mind that just because a sequence is not monotone does not mean that it diverges. It might still converge. Yes. No, so I didn't say that 0.19 repeating is less than 0.2. I said that every term in the sequence is less than 0.2. Yeah, and 0.9 repeating, if you did a sequence of 0.9, 0.99, 0.999, that's infinite. Every term in the sequence is less than 1, but the sequence converges to 1. Yeah. Okay, so let's look at another sequence. I have 3/8, 5/13, 7/18, 9/23, 11/28. We want to find an expression for the general term a sub n. An explicit formula, not a recursive one. So let's just look at the numerator. And remember y equals mx plus b? Okay, so every time I go to the next term in the list, I'm adding 2, right? 3, 5, 7, 9. I keep adding 2 over and over. Which part of a line is that is that 2? Is the m, yeah. Okay, so my numerator, I'm going to say is 2x, and then what would the b? B usually represents the first term, right? Yes, I'll put a plus 3. And then I'm supposed to use n as my variable name, not x, so I'm going to do one more. So I'm going to write, change the order, 3 plus 2n. Say that's the numerator. Okay, then let's look at the denominator. It's just a separate list, right? So 8, 13, 18, what are those going up by? 5. So that's my slope. So if I'm looking at y equals mx plus b here, this is going to be 5x plus the first number is 8. But I'm supposed to use n, not x, as my variable name. So we'll do the 8 plus 5n. Okay, so we should check that when we put in a 1 for n, we get the first number in the list, right? What happens if you put in a 1 for n? You get the second number in the list, right? If you replace all your n's with a 1 to try to calculate a sub 1, you get 5 over 13. Replace those n's with 1s, which is the second number in the list. Like, oops, we're off a little bit. So to fix it, I actually want to replace these n's with n minus 1s. And then check. So that didn't work. Now let's try A1 if I do the n minus 1 trick. So 1 minus 1 is 0, so this becomes 3 plus 2 times 0, which is 3. And 1 minus 1 is 0, so this becomes 8 plus 5 times 0, which is 8. So that does give me the first number in the list now. So that is my general term. All right, I want to look at the limit of that a sub n. The limit as n goes to infinity of a sub n, that expression. So I'm going to simplify it. I'm going to distribute my 2 and my 5, combine like terms. So I get 2n plus 2 over, wait, that's not right. So it's 2n minus 2 and then plus 3, so it's 2n plus 1 over 5n plus 3. What is the limit as n goes to infinity of 2n plus 1 over 5n plus 3? Yeah, 2 over 5. So that is one of those pre-calculus things you learned about end behavior. When you have a rational function and the numerator and the denominator have the same degree, the limit is the ratio of the leading coefficients. All right. One last concept I'm going to show you is a quick detour. We're not really talking about sequences. This is the Algebra of Factorials. It's going to be helpful in an upcoming class for you to already be a little bit familiar. So we kind of threw it into this lesson. All right, so the main idea with simplifying quotients of factorials is to find the factorial that's bigger and write out the first few factors of that factorial until it catches up to the smaller factorial. Or just write out a bunch of numbers, okay? So who knows what factorial means? Like, Diane, what is it? Yeah, multiply by all the numbers, all the whole numbers less than it. So 12 factorial means 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. 3 times 2 times 1. So that's my numerator. And then my denominator is 10 factorial. So that is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Once you've done this 5 or a million times, you'll realize that you don't need to write out every single factor. Like, you'll start to recognize what's going to cancel. Because this is all multiplication on the top and all multiplication on the bottom, so you can cancel common factors, right? So my 10s cancel, my 9s cancel, all of this cancels. And you're just left with 12 times 11, or 132. Okay, now for the shortcut without writing every single factor down. So 12 factorial over 10 factorial. Which number is bigger, 12 factorial or 10 factorial? 12. So I'm just going to write down factors of 12 factorial until I get to 10, until I get to the smaller one. So I'm going to have 12 times 11 times. Now the rest of 12 factorial is 10 times 9 times 8 times 7 all the way down to 1, which can be written as 10 factorial. Okay with that? Right. That's over 10 factorial. And then the 10 factorials cancel, and you get 12 times 11, or 132. Just saves you not having to write down every single factor. Okay, same concept, except now we've got some n's in there. And I want to simplify this thing. So I have 3n minus 7 factorial, and then 3 times n plus 1 minus 7 factorial. So I'm going to distribute the 3 and combine like terms. All of that is in parentheses, so I'm just going to do all that first. So my numerator is 3n minus 7 factorial, and that is squared. And my denominator, that's going to be 3n plus 3, and then subtract 7, so you get 3n minus 4 factorial squared. All right, what number is bigger? Which, for any value of n, positive number n, which is going to be bigger, 3n minus 7 or 3n minus 4? 3n minus 4. Yeah, the 3 n's would be equal, but if you subtract 7, you get, it's going to be smaller than if you subtract 4. So the 3n minus 4 is bigger. So let's start in the denominator writing out the factorial for 3n minus 4, because that one's the bigger one. Start with the bigger one. So 3n minus 4 is the first factor. And then what would come next? Three n minus 5. One smaller than 3n minus 4 would be 3n minus 5. The next integer down would be 3n minus 5. A number that's one smaller than 3n minus 4, 3n minus 5. What would be the next one? 3n minus 6. Yeah. Yeah, the whole expression is being factorialed. Yeah. So 3n minus 4 factorial. So you want to start with 3n minus 4, then multiply by a number 1 smaller than that, times a number 1 smaller than that, times a number 1 smaller than that. So 3n minus 4 is just some number. Well, eventually you'll hit 1. Eventually you'll get 3n minus something that gives you 1. Yeah. Yeah. Yeah, if you keep subtracting 1, so 3n minus 4 is some positive integer. If what's negative 1? Oh, if 3n minus 4 was a negative number? Oh, it won't be. It won't be. Yeah, that's a good point. I should specify that n is 1 is always a positive integer. Yeah. N is always a positive integer, then and eventually the reason we're practicing with this is that we're going to take the limit as n goes to infinity. So n is going to be really big, and 3n minus 7 will be positive. Does that make sense? Okay. Okay, so 3n minus 7 is the first number, sorry, 3n minus 4. One smaller than that is 3n minus 5. One smaller than that is 3n minus 6. One smaller than that is 3n minus 7. And that's the magic thing I was looking for. That matches the number on top. So factorial to get to the end. And then in the numerator, I have 3n minus 7 factorial. Now, both the top and the bottom were being squared. So I'm just going to square the whole fraction. instead of squaring the top and the bottom separately. And so now I cancel my 3n minus 7s. 3n minus 7 factorials cancel. And you're left with 1 over 3n minus 4 times 3n minus 5 times 3n minus 6. And then all of that is squared. So you would square the top and square the bottom, and squaring the bottom would mean squaring each factor. Squaring 1 would still give you 1.